Okay. So anyway, um, I have uploaded the quiz for you for the basic math. So you can check on the Google Classroom. But when you open the link, please make sure you are ready to finish the test, because if you are not finishing the test, uh, and then you close the quiz, and then when you want to enter again, attempting to work out the quiz, then I don't think it is possible, because I make the limit for the attempts to be only once. Okay, so be careful. Be careful. Okay. Okay. Yeah, I check that. I think only three students taking the quiz, and yeah, I hope you can take it before tomorrow morning. So I hope today, at least at night, you can check it out. Okay. Or if you have time tomorrow morning, morning time, Taiwan time, before 9, I think you need to take the quiz. So at least at 8 a.m. is still, I think, the last attempt for the quiz, because you need at least 30 to 40 minutes, or even 30 minutes, for the quiz. Okay, let me remind you here. Okay, don't forget to take the quiz. Okay. Okay, let's start our lecture. Okay, before we start, let me review what we have done in the feedback time last week. The function f function is this. This is the function, and write the vertex coordinate in terms of, you need to have a bracket and then the number, and then close the bracket. So there are two methods to see the vertex. One method is just directly using the formula minus b over 2a, and then you can easily get this is 1, and then you put 1, and it's equal 1, and you can write 1 1, or you can complete the square, make it into the x minus h plus k, and you can directly write 1 1, or this is h. Okay. Okay, another question is calculate minimum value. Minimum value is when you have, let's say that the graph, if you have minimum value, one possible graph is like this, right? So which means the minimum value is actually, so if this is, let's say, a b, so the minimum value is actually the b is equal. Okay, so if we look here, we basically looking for the vertex, and then plug in the value of the vertex the x value, and then you can get this is actually 1. Or you can look up at the the, the, the complex square, the standard form. So you have hk, which is 2 and 1, and you will see that directly this is the answer, 1. Minimum value is 1. Okay, and only one person get correct answer. Okay. Okay. Okay, any questions from last week feedback time? Okay, I hope you get it. Okay, the vertex, the minimum value or maximum value, how to make the complete the square. Okay, that's very basic, and that is very important for calculus. Okay, if there's no question, let's move on to the next sections. We still are at the polynomial functions, but we will get into more details. Okay, so today, let me start with the uh, general terms on polynomial function of some degree n. Okay, okay, this is all the terms that usually we are going to observe or we are going to see, uh, because polynomials, it can be really long. For example, you have 3x with power of 5 plus 6x4 minus x cubed plus 3x squared plus 4x minus 5. This is we call polynomial function of degree of 5, okay, because it's the greatest value of the power is of the degree is 5. Okay, so this is polynomial degree 5. This is the leading term. Okay, leading term. This is leading coefficient. And this all have each coefficient. This is a constant term. Okay, I think this is just a terms, just terms that usually on a polynomial, not necessary to be memorized. Okay, as long as you can just analyze from a polynomials. Okay, and I think you're already familiar with the functions, with the equations, so I think that should be okay. Let's see our basic polynomial. Okay, so this is all we say. We call this. They are monomial because they are only having one certain aspect of the degree. Okay, so it's not like x squared plus 3, right? So it's just x squared, x squared, x cubed, x4, x5, or we can say all are monomial, and they are all basic functions. Okay, so if we are looking here, we start from linear functions and then quadratic, and then the cube functions here. If you see the cube one, it will have the negative here, negative area. And then back to x to the fourth, it's looking like x squared, but different different area here. it's more flattened. Okay. And then you get the also the x with 5. It's also similar with x cubed. You will see that nearby the x-axis, the line is getting leaner. It's getting more flattened. Okay. If you increase the degree, like for example, you get the x6, x8, or x7, x9, it will be more flattened and flattened and flattened. If you check the GeoGebra, try to draw the graph, you will see that it's going to have more flattened. Okay. Okay. Now the graph, of course, we have learned the transformations, and we can also transform the polynomial. So if we look here, we can transform this x cubed, okay, and then transform to the y-axis, and the the blue one here is the original function. Or let me write here is the this is x cubed, and the red color here is the mirror or the reflections of the x cubed. This is also similar. We see the original function is here. This is x with the power of 4. And then it is the horizontal shift. You'll see the vertex. Okay, the vertex at the beginning is at 0, right? And then it's -2, which means -2 is +1 +2 to the right, right? So here is the transformation here. So this is now the vertex, and making the same graph with the red color here, and it's become x minus 2 with the power of 4. Okay. And similarly, we also see this function here. The original function is actually, let me draw, it's not written there. It's x with power of 5. Let's say this is x with power of 5. And then it's minus, so it's mirror to y-axis, becomes the blue one, and then multiply by 2. Multiply by 2, and then it's you will see multiply by 2 with the red color. So from the original one here, so the original one is the minus x5, and then multiply by 2, it's become the red color, and then plus 4. So it's going to go 1, 2, 3, 4. Okay. It's plus 4. So all the transformation you have learned before, you can apply also with the other polynomials. Okay. Let me write here a transformation of polynomial. And from the calculus part in our lecture, we learn about continuity, right? So this is also similar with the continuity idea. The graph of polynomial function, they will be smooth and continuous. It should be. So it is has a smooth curve. Okay. No corners or sharp point. So these two are polynomial function. So if you look at this graph here, this certainly not a polynomial functions. Maybe it's a mix, a polynomial mix with the other functions, and then it, like for example, if you have the piecewise defined functions or polynomial, but you have equations, and then it became the rational functions. Also, you will have the asymptote, right? And then it's make the graph broken. Or even if you have like the corner here or the cusp, this is also not the polynomial function. And the important thing in polynomial here, if you look at the graph, when you are approaching the x-axis, to the right and to the left, so x goes to negative infinity, x goes to infinity, you will see that the x can be anywhere, which means the domain can be any numbers of any real numbers, right? And the end result, if you are having the, for example, if x approaching negative infinity, what happened to the functions? It's probably going up, right? And this also, if you're going to the right, is also going to going larger and larger. And here is another possibility. If you have x approaching negative infinity, and you will see that the f is actually going down. So you can say that the results, f is getting negatively large, and this is x going to infinity, and the functions is getting larger and larger. Okay, we call this, okay, this results here, all this result, we call this is the end behavior. Okay. Okay, let me go for details. So this is the end behavior of polynomials in more detailed informations. We can see the end behavior by looking at the degree. Okay, if it is odd degree or even degree, there will be a difference in the end behavior. Okay? I think you already get the idea. Okay, you'll see here if you have from here, it's getting infinite positive, right? And if you're getting here, it's getting negative infinite. You have also the mirror image. If you get here, it's going to have positive infinity as x is going to have negative, and going here as x going positive infinity, the functions will going down negatively large. And if you have a even degree, you have both going to the same y, right? Going to the positive infinity, both of y. Okay. And here you can go down. Okay. This is the mirror image. So for example, if you have, for example, some polynomial functions, and then you have okay, by looking at this polynomial here, this is even degree, right? So even degree, and then you have the negative part here. So probably it will be like this, right? Probably. To be precise, the graph will looks like that. So it will have the, yeah, probably like that. You will notice if you are checking any functions that are polynomials and then try to see with the graph, and you will notice that when you are dealing with like x4, x cubed, x, and a constant, at least if you're looking at the x with the power of 4 and x cubed, you need to combine at least two property from those polynomials. You have the even degree, so which means the whole graph, if you look uh, at the whole picture, it will at least like this, right? But it has x cubed, so it should be having some x cubed property, which is x cubed property is like this, right? And you will notice that at the middle here, you'll see some part of the x cube will be shown. Okay, so you can check with the GeoGebra if you want, and check other possibility also. And because we are talking about n behavior, we can also write the n behavior is this. So as x going to negative infinity, the function will also going down. Okay. Okay, that's the end behavior. I think in practical, I think you already mostly learn when we deal with the limit at the calculus, right? Okay, real zeros of polynomials. Okay, so if p is a polynomial and c is a real number, then the following are equivalent. C is a zero of p. So 0 means the solutions. Okay, so in polynomials, you will see the terms. Let me write the terms zeros. Like for example, if you see the x minus 2, x plus 1. Okay. So you will see the constant here. This is ours. So c is 2. So c is a 0 of p, or we call the solution. So zeros is any constant that causing 0 to the whole equation. We call usually zeros. And x is equal c is a solution to the equation. Okay, that's basically what zeros means. X minus c, we call this is a factor of the functions, factor of the polynomial functions. And then if we draw in the graph, we can also conclude that c is the intercept, x intercept. So when you have the let's say the easy one is the quadratic. You have the quadratic. When you have, like for example, this one, you have 1, 2, it's crossing directly 2 point here, right? Because you have two solutions. So the solutions mean if you are factoring the quadratic functions, that is the one that are making the intercept on x-axis, right? Okay, this is just adjusting the terms on polynomial functions. We are usually using the zeros to get the idea that that is actually the solutions, okay? Or the one that making 0 to the whole equations. Because we will go more details, not only quadratic, we will have the x cubed, x to the 4, x to the 5, and so on and so forth. Okay, because we are dealing with some value that are actually the intercept of x, then we also have, I think you also familiar with this because it's also on the calculus. There will be an intermediate value for polynomials. And it's actually similar with what we have learned in the calculus, but actually you need to learn here first. So imagine you will see, or you will observe the functions p from a to b, okay? And you'll notice that when you have this point here, let's say this is point of a, pa, and point b, pb, the point are, for a, the point are negative, right? And b, the point are positive. So in between a and b, there should be c that is actually in between, okay? So, or in our case, in our polynomials here, we can say that c is the one that is zeros, that makes the whole equation 0. So if p is a polynomial function and pa, pb have opposite signs, so it can be positive, negative, or negative, positive, then there will be a value c, exists one value c between a and b, for which when you are evaluating those c, it will be 0 for the whole equation. Okay. So that is the intermediate value of theorem. Okay. Now, how to graph using this theorem and also the previous theorem? For example, if you have a polynomial functions, let's say I will just directly using the factors. Okay, now we are seeing the results for the zeros directly from here. So zeros will be -2, 1, and 3, right? And we can use if you want, the line interval to get the idea on how the graph will behave or looks like. Okay. Now we can mark this as -1, -2, and then This is 1, and this will be 3. Okay. Now, what should we do? We can try some numbers to see how the graph will be. Maybe from here we can check check x equal -3. Check here, -3. It's -3, -3. What will happen? Negative, negative, it's positive. Let's multiply with negative one more, it's negative. So the whole thing here is negative, which means the graph is below x-axis. Okay, and you have -2, 1. Maybe you can check 0 or check -1 if you like. You get positive, negative, negative, negative. It's positive. So graph is above. And we can check also here x equal 2. It's positive, positive, negative. It will be negative. It's below x-axis. And check again, maybe 4, just to make sure. Positive, positive, positive. So all positive. So based on our testing here, we can check some value, some other value that are easy to evaluate. For example, -3, -2, -1, 0, 1, 2, 3, 4, and check the functions. So plug in 6, 0, -4, 0, and 18. So at least from this and from what we have tested for the signs, we can get the idea of how the graph will looks like. So less than -2, it's negative, right? So we can draw that it goes under here. This is for p -1, it's greater than 0, right? This one. And then it's going all the way down here. And it's crossing the 1. And then it's probably going here. Going here. And then going there. And this will be, let's say this is P4, and it's 0. And maybe this is the P -3. This is less 0. This is P2. This is also less 0, that we are actually all these points that are already we confirm with the line number. Okay. But in more details, how to graph like many functions, the one way to easily graph is using calculus, but you will get that idea later on calculus. The basic math, this is just our approach, okay, our easy approach to check how the graph will behave, okay, whether it is in negative area, positive area, and how it looks like at the end of uh, the graph, okay. Okay, I think we can move on. And yeah, this is just a reminder that we will have also, we call the local maximum, local minimum, or maxima or minima of polynomials. And whenever you see this that have the maximum point, we call the local maximum, and this will be the local minimum. Why it's called, we need to use the local here is to make sure or to confirm local means restricted on some domains. We can say just maximum or minimum point on all real numbers. And there is a one theorem that are actually this is quite reasonable. So if you have a polynomial of degree n, then the graph will have at most n minus 1 local extrema. For example, you have quadratic. This is degree 2. The local extreme point or local extrema will be 2 minus 1. So we will only see 1 point here or 1 point here. Okay, only one local extrema. This is example for if you have family of polynomials, and you'll see that the c here, the constant c here at the variable x squared. This is what I told you before. So this is a degree of 3. So this is p is degree of 3, which means the original function or the whole functions, when you zoom out the graph, you will see it at least like that. And of course, you will see that when you are increasing c from 0, which means you will have first is this, c is 0, and you will see this, you will see this, and you will see this. When you increase c, you see here, notice that from 0 to 1 is not really significant. It's just a little amount that going here, right? And then c increasing 2 is going here, right? And c equals 3 is more and more going here. What is this curve about? This is actually an x squared. Remember that x squared you have like this, right? So in between of this whole degree of 3, you have a behavior of quadratic functions, okay, like I said before. So if you mix a graph, okay, then you will have at least some behavior of that part of the graph in your whole picture, okay. So this is actually the x squared, okay, that are part of the whole cubic or the whole polynomial degree 3, okay. Okay, that's I think the intro for so for the general polynomial. So the first one is intro for the polynomials that you have familiar with, the quadratic functions, and then this is in more general. You can have polynomials in any degree of 2, 3, 4, 5, and so on. Okay? And then you have some terms like zeros, factors, okay? And the next section is actually more, I think the necessary one is the next section. This is about the dividing polynomials, okay? Or division algorithm. Okay. And I think you also have learned before. So I will straightly go for the definitions. Okay. So the definitions here, if we have P and D, they both are they both polynomials, and with D is not equal 0, and there will be another polynomials Q and R, where R is, it can be 0 or degree less than degree of D. And we can write that here you have a rational P over D. Okay, you will have Q plus R over D, or or you can write in these terms. You can write Px equal dx qx plus rx. This is we call the dividend, divisor, quotient, and remainder. Okay. Dividend and divisor, if you are maybe mixed up or not sure on how what it is, this is not necessary to be remembered. You know that this is the polynomial that you want to divide. That's fine. The one you need to remember is the quotient and remainder. Okay? Because we will always mostly observe the remainder. Okay? For example, if you have the divide 6x squared minus 26x plus 12, divide this by x minus 4. The first way to look at this function here is we call the method is long division. Okay. So first, it's just like regular division. Okay, but we are dealing with polynomials now. So what should we do now? Look at the variable. We have polynomials degree 2 here, the highest one, right? The polynomial degree 2. This is degree 1. So which means to get this value here, we need to multiply with 6x actually, right? And we need to multiply with this and then put the results on the bottom of this whole functions. So this will be 6x squared, and 6x minus 4 is minus 24x. That is our results. And then subtract. This will be cancelled. This will be negative 2x plus 12. Now we have the same degree, so we are just multiply with the constant. we multiply with -2. So we have -2x and plus 8, and then subtract. So 12 minus 8 is 4. This will be the remainder. And this will be the quotient. So we can write the whole thing here. So this will be the quotient. This will be the remainder. Okay. Or we can also write so remainder here and quotient here. And this is diffuser, dividend. Okay, any questions first? Okay, if there's no questions, let me continue and maybe giving you some example. Okay. So you have px is 8x with the power of 4 plus 6x squared minus 3x plus 1. And you have dx is find qx and rx such that okay, you can try to solve this. This is basically, you can say that you need to divide p with d to get q and r. But I'm writing in other terms that actually similar with our definitions on the long divisions. Yeah, you can try to calculate first and make yourself familiar with the long divisions. If you forget, then you can try to check. You can start writing the 8x with power of 4 plus 6x squared minus 3x plus 1 divide by, okay. I hope the method here are understandable or easy to follow. It's just using regular divisions, but we are not using numbers, but we are using the polynomials. And then when you are dealing with this, please make sure that your calculations, like positive signs, negative signs, are correct. If not, then when you are dealing with the final results, you will get maybe some mistake. Okay. Guys, let's start with we have 8x fourth, and we have 2x squared, right? So we need to multiply with at least 4 and x squared, right? So that we will have 8. We'll have 8 x raised to the power of 4th. And we need to multiply the rest of it. So we'll multiply with the minus 4x cubed, and then plus 8x squared. We subtract this, cancel this. Now, something that maybe you will have mistake here. You have this cube, right? And you don't see any cube at the top, but that's okay. You can start with 0x cubed. Yeah, it's 0, right? So 0 minus 4x cubed. So 0 minus minus. So we'll have a positive 4x cubed, right? Okay. And then 6x squared minus 8, it will be minus 2x squared. And then we have minus 3x, and then plus 1. Now we have x cubed. So we need to multiply once more with x, at least x, and then we need to also multiply with 2. So we need to multiply with, this is plus 2x. So multiply, and we'll get 4x cubed, and then minus 2x squared, and then plus 4x. Cancel, and this also canceled. So this will be minus 3 minus 4 is minus 7x plus 1. So we will get that this is our remainder. This is our quotient, our qx. Or we can write in terms of 8x fourth plus 6x squared minus 3x plus 1 is equal with this is px dx qx rx. Okay. Okay, any questions? Okay, no, right? Okay, let me give you one more example, and then we will have another way to solve these long divisions. Okay. Let me just write this: divide by x minus 3. Yeah, you can try for a few minutes, and then I will solve. Okay. What is the remainder? If you already finished, you can write the answer on the chat box. Minus 3x plus 5. Jordan, that's correct, but that is not finished yet. You can still one more time. And I think it's not negative 58. I think you make a mistake in the middle, I think. But Jordan, for Jordan, you are correct, but you need to continue the calculations. It's not finished. Yes, minus 4. That's the reminder. Minus 4. Okay. So if we are looking at the long division here, you will start with 2x squared to make it 2x cubed here, and then minus 6x squared, and then subtract this. Minus 7 plus 6, so it will be minus x squared plus 5. So it should be minus x, and then we have minus x squared plus 3x. So we'll have minus 3x plus 5. And we're still not finished yet. We can still have this x the same degree, right? We can still cancel that out. This is negative 3x plus 9. So we will have minus 4. And this will be our remainder. Okay. long division is probably the easy way to see how the polynomials directly divided, and then we can find the quotient and the remainder. But sometimes it takes some steps here, and maybe long, because it's called long division, so it should be long process, right? So there's another way to look at, and it's called the syntactic divisions. And I believe you already learned this before, but let me just make it some review for you. Okay, let's write the functions first that we are going to define. This is the functions, okay? So first we write to the coefficient of the polynomials, 2, -7, and then there is 0x, right? So 0 and 5. So all possible polynomials coefficient we are going to write. And then divide by, it should be divided by x minus 3, right? But we know that x minus 3 is actually, if you remember the factors, then we can say that this is actually x equal 3 if you are thinking of the zeros, right? So we can write just 3 here, not x minus 3, okay? And then what you can do is first look at the first coefficient, 2, going down here, make it 2 like that. And then multiply this 3 and 2, becomes 6. Write 6 here, okay? And then this become -1, right? We plus this become -1. Multiply with 3, and this will be -3, and this is -3. And make it all the way here, and it's -9, right? And it's -4. So we have, this is our remainder. And this will be the quotient. We can have 2x squared minus x minus 3. And it's the same as in our answer here, okay? This is called the syntactic divisions. And I think this is practically easy, and it is also useful if you're dealing with complicated math, like in calculus also. This is pretty useful. But there is one weakness. Do you know what is the weakness of this syntactic division? Anyone know what is the weakness? Yeah, any method. Any method, Helen. You can choose any method. But long division and syntactic division both have pro and cons. Okay, what's the weakness of syntactic division? It seems really easy, right? Really easy, and you get directly the answers. But there's actually one weakness. Anyone know or can point out? Can you point out which one it is? Which what is the weakness? Oh, good questions. How do you know which of the quotient will have x squared x? Okay, it's from the number of the coefficient. For example, we have this is 1, 2, 3, which means it will be a quadratic. If there is only 2, there will be linear. If there is 4, there will be a cubic functions. Okay, got it, Scarlett? And it's always like this will be x squared x, and this will be a constant. Okay, and that is how. Okay, so one weakness that is I think it's quite obvious. What's happened? This is x minus 3, right? And you can write 3. What happened if you have x squared minus 3, 3x, let's say, plus 4? If you have this, what can you write in these terms? Difficult, right? So that is one weakness of the synthetic diffusion. You need to have at least polynomial degree 1 only for the diffuser, or this part here. So it should be x minus 3, x plus 2, x plus 1. Then you can divide with synthetic diffusion. But if you have like this case here, you have like polynomial degree 2, then you need to use the long diffusions. Okay. And that way, I think you can make some strategy which method you can use, right? So if you think that this is easy, then whenever you have the diffuser is just polynomial degree 1, then you can use the synthetic diffusion. But if it is more, then you need to use this. Okay, the long diffusions. Okay, now any questions? Okay, if no, then let me go through to the next sections. It's more about the theorem on remainder. Okay, first we have the remainder theorem. Okay, if the polynomial px is divided by x minus c, then the remainder is the value of pc. Okay, how do we get this? This reasoning is logically correct. Okay, so if the diffuser is the form x minus c, okay, for some real number c, then the remainder must be a constant. Since the degree of remainder is less than diffuser. If we call the constant r, then This is how it should be. And if we are going to replace x by c, we get pc is c minus c q c n plus r. So pc will be just r. So that's what it means. Okay, that's what it means. So in other word, okay, in other word, uh, in the early introduction of the quadratic or polynomials, you know that there is a zeros, right? The solution for x, okay, and that is actually, if you can factor out the from the functions, then you can use from the factor. Okay, we have the solution. For example, if it is x minus c, then the solution of x will be c, right? When you plug in c, it should be 0. Okay, but in terms of in general polynomials, when you plug in c, there will be some part will be 0, and there will be the number that's still there remain still at the function, because it's not completely divided and become 0, right? And that number is actually our remainder. So what this means is, when you are having divisor x minus c, okay, and um, you need to find quickly what is the remainder, you can plug in c into the functions, into the whole function itself. That when you have this pc, then this is actually your remainder. Okay, this is very, very important, because it helps you to pave a way on the early quadratics, finding zeros, and then now you have the remainder. Okay, and from here, actually, you can see that, oh, right, this is what makes zeros, right? This is what makes zeros. And because it has general polynomials, that not all polynomials has a 0, right? So it has the remainder. So when you divide, it's not completely divided, but still have some number that's still there, and we call that remainder, right? So in these terms, we have this: if the polynomial can get divided, completely divided, there's no remainder, right? So we can say this will be 0 if p is completely divided. I hope you can connect all the things you learn from the quadratic, general polynomial, and then now all of this remainder theorem. Okay. There's also another theorem, but let me give you another example on how we are using this remainder theorem. Okay, let's say example, we have px. This is equal 3x with power of 5. Find, let's say, quotient and remainder when px divided by x plus 2. Okay, so if you are using the remainder theorem directly, we can get easily that when you get, or when you evaluate at x equal -2, that is from the factor x plus 2. If we plug in and we calculate, maybe it's too complicated to calculate, but I assure you this is 5. Okay, to make sure that this is correct, we can always go back to syntactic divisions. So we can write 3, 5, -4, 0. Don't forget that if you have, for example, you need to have the quadratic, but it doesn't appear here. You need to write 0, and then 7, and then 3. Okay, and then divide by -2. Start with 3, and then -6, 3, -2, -6, -1, 2, -2, 4, 4, -8, -1, 2, 5. Remember, this is the syntactic division, and you need to plus this, right? Not subtract. Sometimes you mix up with long division. So the last part here will be remainder, which is correct. Same. And this will be 1, 2, 3, 4, 5. So it should be having x, 4, x cubed, x squared, x. So this will be our quotient. Okay. Well, so it seems if you're using remainder theorem directly, you need to have like a huge calculations, right? Huge calculation. So that's I think one way to think which way you are going to solve, or you are going to approach. I think if you have like the polynomial functions that are easily to be calculated, I think that will be better if you are just using this remainder theorem, especially if it is asking only what is the remainder. So you can just plug in the divisor, and then you can get the answer directly. The other theorem that I think important is the factor theorem. So C is a 0 of P if and only if this x minus C is a factor of Px. I think that's reasonable. So if Px factors as Px is equal x minus C and Qx, then when you have PC, then it should be 0, right? Because that the results should be 0, right? If PC 0, then by remainder theorem, wait. We are going backwards, and we are seeing that it's going back here. So x minus C factor of Px. And I think from the sentence itself, from the theorem itself, it's kind of reasonable to say that we can say that the number C is a zeros of P, which means it's the solution of P, if x minus C is a factor. I think that is reasonably correct. I think we can go for a little bit more thing. Okay, any questions first? Okay, if there's no questions, let's move on. I hope you can still follow all of this, okay? Especially the long division and synthetic divisions, okay? The next part is called the real zeros. Real zeros of polynomials. Let me copy some graph first. Okay. 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 So we'll start with it's called the rational zeros theorem. Okay. So if we have polynomials px, it has general equations, and they are having integer coefficient, okay, where the an and the last, so the first term and the last term is not equal 0. So it should be having some coefficients there, some number. Then every rational zero of P is of the form of P over Q, where P and Q, they both need to be an integer, and P is a factor of the constant coefficient of the last term. So this is the last term, and Q is the first term. So if we are going to prove whether this is correct or no, so let's say if P over Q is a rational zero, in lowest terms of P, then we have an P over Q with power of n plus an minus 1. So we are just substitute with P over Q. And this should be 0 because we say that if P over Q is rational 0, so this should be a zeros. And we multiply with Q over with power of n. So we will have an en plus and factorize the P. So an P n minus 1 plus P n minus 2 Q plus should be equal with negative a0 qn. Okay, now p is a factor of the left side. So it must be a factor on the right side as well. So, and since p over q in the lowest term, p and q have no factor in common. So p must be a factor of a0. And you can also try to make another expression with a factor of q. Similar proof shows that q is factor of a. And this is just to prove that what we are saying here, that every rational zero of p is of the form p over q. So we are checking p over q, use the general terms, and make that actually true. Okay? So we are saying that this is a factor now. P is a factor. And if you are factoring out the q, and then you can see that also q is a factor of the an. And p is a factor of a0 here. Okay. Let's see. This way, okay, this rational zero theorem, it can help you at least you can have some guesses, and especially it will be much more faster when you have simple functions that you can think some of its factors probably. So let's try. Okay, for example, find rational zeros of px equal x cubed minus 3x plus 2. Okay, now to check whether we have zeros and how many zeros we will have, we can check with our p over q. So p will be here, and q is here. But p and q, this should be a factor of 2. This is factor of 1. What does it mean? So we can think that factor of 2, we can have plus 2 or negative 2. For 1, we have plus 1 or negative 1. Oh, factor of 2 is also plus 1 and negative 1, sorry. Okay. So you can have plus 2 and plus 1 to make it 2, or you have negative 2, negative 1 to make it 2, right? Factor. Okay, now With P over Q, then you will have at least P over Q will have +2, -2, +1, and -1. We have these 4 possible factors, or possible number as a factor. Then we can try one by one, because it's I think it's simple calculation. We can try P with 1. It's 0. So we directly get 1 of zeros. We check again with -1. This is 4, right? And check again with 2. This is also 4. And lastly, we check -2. This is 0. Yeah, 0. So this will be our 0. So the rational zeros So this is one way to look at. Another way, if you think that when you plug in 2, you feel lazy to calculate, or maybe you feel that this is too much calculations, then you are doing 1 here. I think 1 is okay, right? And then you get 0. What does it mean is, then you can divide with x minus 1, right? You can divide with x minus 1. You can use syntactic divisions. So let me write x cubed minus 3x plus 2. So 1, -3, 2, and divide with x minus 1. So divide with 1. This is 1. This is another 1. So this will be -2, -2, and okay, this is pretty much completely divided. The remainder is 0. So we'll have x minus 2. So we have, oh, sorry. This should be, 1, 0, -3, 2. Okay. So this is 1, 1, 1, and then this is -2. Okay. Should be x squared plus x minus 2. So we will have x cubed -3x plus 2 is equal with x minus 1, and then x squared plus x minus 2. I think we can factorize this. Of course, we have x equal 2, x equal 1, and x equal -2. So this is our zeros. Okay, we can look at this method also to check whether we have our zeros or not. And you can also check with some trial and error. Try some numbers from the factors here from P over Q. Okay. So remember, this is P, Q. Okay. Okay. Now, as a conclusions, or as a summary for the method, how would it work, or how you can use it? Let me write some guidance for you. Some guidance. So finding rational zeros of polynomial. First thing to do is list possible zero. This is using the P over Q, and then check whether how many zeros we will have, and then divide. If you are seeing that, oh, I know some of them, and then we can divide. Okay, we can check with the long or synthetic division as we have done before. And then the third is, yeah, repeat the activity. So repeat step 1 and 3. Okay, if you have like maybe long polynomials, you can repeat and then until you find all of the zeros. Okay. Okay. Any questions? Okay. Actually, okay. Let me check. Okay. So I don't see Blessing now. Anyone know where he is? Because until now he is not joining our Google Classroom for basic math. He joined the calculus, but he is not joining the basic of math, and he sent the wrong assignment. So he sent the basic of math and then sending to the calculus Google Classroom. I already told him, but I'm not sure why he's still not be able to join the Google Classroom for basic of math. And also, I check. Let me check the. So I check the one who are joining the quizzes. There are 3 person now, but I'm not sure why. I see Hans. Yeah, you hear right? Hans, you joined the quiz, but I think you closed the platform, right? So that's why until now it's not finished yet. But can you try one more, because it appears that you already logged in, and try one time attempt. I'm not sure whether you can finish the quiz. So Hans, you need to better check out the quiz, okay, maybe at tonight, because I see your name in the report. Okay. Yeah, the quiz is actually I'm not say it's difficult, but you need to be focused. Okay, so first you need to be focused, and because each questions of the quizzes, there will be a timer. Okay, so why I need to make each question has timer, and it will have different timer. Different timer because each question has different time limit to solve. And why I need a timer is to make sure that you are focused on that question, meaning you are focused working on your quiz, not maybe discussing with others or maybe distracted to with other things, so that you can focus on just the quiz itself. Okay. And this is just a trial for this platform. I'm just using it right now, and hopefully you can get to be more familiarized. uh, I think I'm not using some of the features, such as there is actually like a bonus point, like a game. Like for example, sometimes you will get a bonus like immunity in the quiz, so it's like a game actually. So when you get the immunity, when you write the wrong answer, you will get one more chance to get your answer correct. Yeah, it's like a game. You can get like some bonuses, but I think I've turned it down for now. But later maybe I can turn it on, and you can have like maybe like a playing a game. So you have like sometimes you will get like double bonus point. So when you answer the questions, you will get double points. But when you get wrong, you are minus doubling the minus. You will get minus point. Yeah, it's like a game actually. But I'm turning it off, I think, for now. Maybe later I will turn it on so that you can have more like a game. Usually, if something played like a game, maybe you will be more excitement for you, probably. Okay. Okay. Is there any questions? If there's no question, I think I will end here, until here. The rational zeros of polynomial. We will continue tomorrow. I think tomorrow we will be more example on this rational zeros, and I think finishing the rational zeros tomorrow. And then, yeah, I hope to see you soon at the university, Taiwan Tech. Okay. I think the last students who will come for the international student will come on December, right? Or is there anyone who are not coming? Or the last one is December, right? Am I correct? So for this class, what is the latest expectations for arrival? November or December? Yeah, December, right? I think most of you are December, right? Yeah, December. Yeah, I think so, December. So because actually our class is designed as PBL class, which means it's I think in your high school you also use this kind of terms, uh, problem based learning or project based learning. So which means that we will have some assignment, like final assignments, aside from the quiz exam. Like the assignment is it for me personally, I want to help your score from that assignments. And it assignments, it can be any project that you can think of, but I haven't set the requirements yet, but that will be your final assignment. So you will have like an oral presentations for your project in basic of math. And hopefully, because December you will be coming, so we can have that on. So several in December, several in January, and then that will be our PBL mode class. So you need to have some discussion first. I think for this class, I can make some group consists of each group consists of 3 students at least, or 3 or maybe 4, 3 or 4 students. Okay. And I will decide the groups later. Okay, so for now, let's go for the feedback time. Let me just set the okay, let me share. Okay, let's try to join and maybe preparing pen and paper, because I think there is some calculations. Not really that much calculation, but there will be a calculation. Okay. Okay, please join in. And I'm using this kind of platform for engagement, for interactives, because we are doing online lectures, and sometimes I'm not quite really sure whether you get the idea or not. And actually, in the classroom also, when I teach offline, I also cannot really see whether the students are understand or not. Like, they may be seemingly to agree, but I'm not sure whether they are understand or not. So I need to create another platform that can have more. I can evaluate more and elaborate more on most of the students. Okay, 6 students. Are we 6 students? I think we have more. Okay, let's just go here and checking your name. Okay, 7. Okay, so only 7 students. I think you are more here. Should be 8. Okay, anyway, let's start. 3, 2, 1. Okay, read carefully. Okay. I put 30 seconds for these questions. I hope that's enough. I think it's too short, right? But I hope enough. True. 1. Okay. Okay, why you answer B or C? All right. Okay, anyway, let's go. Okay, good job, Helen. Okay, it's A. Okay, second question. 3, 2, 1. So find the remainder. I hope 1 minute is enough. And of course, you cannot use syntactic division here. But I hope with long division you get the answer. Twenty, 19, 18, 17, 16, 15, 9, 8, 7, 6, 5, 4, 3. Okay, just random answer. Okay. Yeah, mostly you get correct. -2. Yeah, 3 students got correct. Yeah. Okay, so all right. So yeah, that will be the end of our class today. So see you tomorrow. Yeah, you can leave the Google Meet. Yeah, you're welcome. Yeah, you're welcome. Okay, if you need